Thursday. John was just asking me a question about why his output was having such a low volume. My idea was that maybe he was not shifting over things to the least significant. If you have put it a different way. I'll put it in the code this way. If you have a hexadecimal code that is 8 bits, FF, you could either have it FF00, or you could have it XF00FF, right? And now if you're outputting it as a 16-bit quantity, it's clear that by shifting FF over 8 bits, we get a full volume signal. So what we would expect if shifting is a signal that ranges from X0000 to XFF00, right? And so that would be equal to 65,535 minus 255, right? Because FF would be 255. So 65,535 minus 255 would come to perhaps 62,280 max. So that would be equal to, if you did it in decimal, 0 to 65,280, whereas 0x0000 to x00ff ranges from 0 to 255, right? And XFFFF is equal to 65,535. Let's say in here, base 10. And so if you're making the lower two nibbles, FF, just a minute, please. I just had to hang up on that one. Sorry. So if you make the least significant 2 bits, 2 nibbles equal to 0, then what you're doing is you're subtracting 255 off. So 65,535 minus 255 gives you 65,280. So you're expecting, a different range if you're working with the most significant 16 bits. But then somebody says, but wait, it's a 12-bit DAC. So if it's a 12-bit DAC, where are we? Right? So 12 bits means that it's 0, 0, 0, F, 0, 0, right? So the most significant 12 bits. So this is 4 bits, that's 8 bits, 8, 9, 10, 11, 12. So I guess it's this way. That's a 12-bit DAC. Maximum value would be here. And so that would be equal to 2 to the 12, which would be, I don't know, 1,024, 2,048, 4,096 minus 1. So that would be equal to 4095 minus 1. Sorry, 4,096 minus 1, which is base 10. So that's a maximum range. So what we would like to see is the 8-bit quantity actually shifted 4 bits over. That would actually improve the volume, I think, by a factor of 16. So for a 12-bit, say for a 12-bit DAC, which is kind of where we're at, right? Because if we look at the data sheet for a 4921, which is the variant on the microchip, we're at a 12-bit DAC. That's kind of where he's telling us we're at. But we're only using 8 bits of it, which means the least significant 4 bits are going to be 0, and the most significant 8 bits will be, well, the 8 bits we got in shifted over to shifted over 4 bits, if that makes any sense. Am I making any sense? You can see there's a another question, which was how come it only comes out of one channel? The 4921 is a one channel DAC. The 4922, on the other hand, will give us stereo. But because we only have a single DAC, right? Because the MCP 4921 is an 8-pin dual inline package or small outline integrated circuit, we only get a 12-bit single DAC. So that's the key. And when you look at the block diagram, you can see that yes, indeed, it does have an op amp. But then John asks, but how come I don't hear anything? And the answer is, well, if we look at the current at the output pin, and this is like, real engineers read the data sheets. I know it's tedious. I know it's sometimes a little boring and your eyes glaze over and all this other stuff, but this is what real engineers do. It says current at output pins is 25 milliamps, right? So what are we trying to do? Well, let's think about this. We're trying to drive 8 ohm speakers with 1 volt peak to peak. Well, wait a minute. 8 ohms, E equals IR. E is equal to 1 volt, and R is equal to 8. And so if I take 1 and divide it by 8, I should be able to get my current, which is 125 or 0.125 milliamps. And this is giving me 25 milliamps. And this is why I say, for your basic 8 ohm speakers, there's no hope of being able to drive these things at reasonable volume. And so that's why I say, look, you've got to have amplified speakers or, a piece, very low power crystal phone jacks or iPod headphones or something that's not going to draw a lot of power, because this thing does not have a lot of power for you to draw upon. And you can tell that right away because of the data sheet, right? He just doesn't have it, in fact, if you look at, current draw, it's measured in microamps. That's like times 10 to the minus 6. I mean, this is little. That's his current draw. So I mean, it's not like he's a power hungry little chip that's going to start driving your living room speakers. He doesn't do that. You need an amplifier for that. So then what we did was we said, well, where can I get an amplifier? I'm in a hurry because I didn't know I needed one, even though I said you needed one like 17 bazillion times. And so then I said, well, let's go on to, Amazon and find one. And I think we found something that could be delivered, like, I don't know, with Amazon magic, same day, right? Although if it was really magic, they'd deliver it yesterday because they knew you were going to, it's like they're psychic. They knew you were going to need it. So if you were looking for little USB speakers, or maybe they were just computer speakers, we'll just say. And then I do a thing where I say prime and low to high, because I don't need to spend a lot of money. See these things, these little buzzer things, they're not going to do you any good. This, free and 1 day shipping, and it gets it there by tomorrow. Get it tomorrow. And here's get it tomorrow. And there's one in here. I don't know. I think it said get it today, but only if you ordered it this morning. So now you have to get it by tomorrow. But still, you know, I don't know, 9.89. Get it by tomorrow. That sounds fine, and that'll give you enough time to sort of test your thing. Now, when I use my touch tone system, I go through amplified speakers that are that have a volume control on them, so I can crank it so you guys can hear it over your over the microphone here. So that was my shtick, and I don't know if you've noticed, but I also provided a 16-bit output. But what he's doing here is he's shifting things over, and I'm not recommending that you use the 16 version. I don't think I use the 16 version. So when you see the DTMF version of this being run, I think there's a write down here at the bottom. Yeah, he does the simple DAC write. So he has this wavetable output. He writes it out to the regular DAC write, and the regular DAC write is in here. And the output byte will be the most significant 8 bits of output on the DAC. And that's kind of what you want. So you'll hear the input should be, I can probably note it in here, output ranges from 0 to 255. And that'll cause, the DAC to range from 0 to 4095 or 4096 minus 1 if you like. So that's that. Now, John, did you say you had used amplified speakers?
Yeah, my computer speakers have that knob on them, just like yours do, but and it worked for the Lab 6 when I recompiled it on there, but it doesn't work for the one that I was using yesterday.
So now when you go to generate your waveform in the DTMF, are you able to print out the maximum and minimum values of your um, of your waveform?
I haven't initialized a serial port yet, so I can do that now and just see if I can print things out. But
Yeah, I think
um,
I think I ended up doing something quite similar. Um, yeah, I do a DTMF generate, and I think that's in here somewheres. DTMF generate. Maybe I should just sort of, there it is, generate. So that comes in. Now my question is, if you've already got this thing working with um, a simple sine wave, then in principle, this wavetable that's over in here is something that you should just be able to play, right? That's already been um, initialized. So if you went to, for example, the constructor on DTMF, you would find that the wavetable in here has been initialized. And so what you could do is you could just play that wavetable. And therein lies part of the issue here. If you're generating the wavetable like I am, you want to make sure that you're generating a wavetable that actually has the full range, right? That goes, this one says the wavetable ranges from 0 to 127. And you can go through the mental exercise now, right? You want the argument to pi, to sine, to be 0 to 2 pi, right? So let's call that theta and set it equal to um, this quantity right in here. Now, if you put theta in here, in principle, you should be able to say, well, look, I is going to range from 0 to 200. So that means that theta is going to range from 0 to 2 pi. So that's good. And you could even write that in here. Theta ranges from 0 to 2 times pi. Right? So that's cool. And in fact, if you wanted this to compile, you might even consider commenting it out because that's not valid code. And then the table ranges from 0 to 200. That's fine. It's going to the max size on the table. Or you could even put in here wave table size. That would have been good. Right? I suppose that's where that goes, because presumably in here somewhere wave table size, yeah, is like 200. And if you were to change it, you'd only want to have to visit the code in one place if possible. So that compiles fine. And then theta goes from -1 to +1, so I add 1. So now it's going from 0 to 2. Now 2 times 63, I think I needed that because of the headroom requirement, goes to 126. I think I wanted to avoid going over 127 or even up to 127 because I wanted to avoid negative numbers in the byte. Probably I shouldn't have used byte to begin with, but whatever. That's water under the bridge. Oh no, it says care. It says care. It should have been unsigned. Well, in principle, you could get this to go perhaps a little higher. I don't know. I thought maybe I adjusted it based on some distortion that I heard. And then, well, the rest is just a dispatch. But if all you wanted to do was play the waveform, right, play this wavetable waveform and see if it's loud enough, you should be able to do that, right? We could even create a separate wavetable player. And then the wavetable player could iterate through the waveform one increment at a time and play that waveform straight out. We could write that, but I think maybe you could write that too at this point. Let's see, what else can I answer? I can only think that maybe there's some sort of a bug, but you can test it for it reasonably well. Somewhere in here you might write home keys, write a program, a method that plays the wave table for testing purpose. Right, and so for that, you'd write a for loop that goes through the wavetable repeatedly, and I would guess you could just do a series of DAC writes on the wavetable. So something like this would be okay, I would think. That should be okay. So I can write use this. And I don't know, maybe just use wavetable of I in a for loop. I'm hard coding everything because what the heck. And then if you're going to do that, might as well make it nice. And so then that would be like your test. So if you could write that, this is an I in here. I don't know if you could see that. It's supposed to be an I. Then in principle, you would be able to see if your wavetable sounds okay. Make sure it's got the right amplitude. Even if you don't have a print statement, you can certainly hear the wavetable and make sure that it's being output properly, especially since you said something like lab 6 is working okay. Are there any other questions about the final project due on Monday, I think, isn't it? Is it due? Let me just check. I'm checking my, let's review. Final project is due 12/9/20, and today is the 7th. So that's like the day after tomorrow. So that's the EE346L project. And we can talk some more about it tomorrow on Wednesday, if you like. Wednesday? It's just, I think. Wait, when does this semester end anyway? Isn't that soon? Yeah. So
The classes are Friday.
yeah, last classes are Friday, the 11th. I'm just going to go through a couple of things here. Let's do a little administrivia. The final is due on the 17th. The final project for EE346L is due on the 9th. And today is the 7th. So that is the day after tomorrow. Would it be helpful if we met at 10 o'clock on Wednesday and discuss any last minute problems you have with the final project? Maybe we should do that, huh?
Yeah, I think it would.
Yeah, I will. All right. I will be here then at 10 o'clock. And anyone who is interested in asking questions about the final project, we will attempt to address the issues. And John, I guess you're getting your speakers by then, I hope. I don't know if anybody else needs speakers, but apparently this is an issue. Let me think about this a minute. And are there any other questions about this final project? All right, then what I would do is I'd like to take just a few minutes to try and do some of these administrative things that we have at the end of a semester. So I've got, let me just make sure I'm on the right course. I've got the 2 links that you need, both in your email and in the course content for doing the surveys for the course. So what I did was I created a link called Survey for the Lab, and I'd appreciate it if you took a few minutes to do that. And then somewhere in here, yeah, here's a survey for the lecture. So apparently these 2 links are not in any particular order. I don't know if I can move one. Can I move these? No. Apparently, I'm Blackboard challenged. So the survey for and I did send this out as an email this morning, not too long ago, perhaps an hour ago or less. So if you do this, and I don't know what happens if I click on it. I don't think they're going to let me submit a survey for myself, which I feel is totally inappropriate, right? I mean, I should be able to survey myself because I think I did a great job. So there. Oh, and I can't go back either. So let me know if those links work for you. Is anybody able to try these links to see if they work? Because they're not working for me. They won't let me submit my own evaluation. Go figure. Has anybody actually tried this stuff to see if it works?
I used the link in your email. Work.
Oh, the email worked. Okay, that's good.
Yeah, it worked.
Great, thank you. So your contributions are greatly accepted. Like us on the IDEA evaluation form. All right, I'm back. That should have been about 5 minutes, and hopefully Everyone had enough time to do the surveys. Do you need more time for surveys? All right, then. So let me just sort of go back to the DTMF program. And I have just plugged this in, so I'm going to check my port. And make sure I've got the right board. Looks like an Arduino Uno. Let's see if the upload works. And probably ought to turn my speakers on. And nothing is working, so there, haha. Well. Oh, there we go. I had to hit reset. So that's nice and loud. So then the question I wondered about, which had to do with let's slow this down a little. All right, so that's okay. Let's see what happens if we look at this DAC right. All right, yeah, we're adding these two numbers together, so that's bound to double the range. Let's see if DAC right is being used anywhere else. There's this wave generator here. Yeah, I don't think we can go any. Let's see, where did we do the initialization? Yeah, I don't think we can do this at 64 because then things will not sound right. Let's try. I guess I have to reset again. Yeah, you can hear the buzzing. But it only happened once. Oh, nope, there it goes again. Yeah, it's not sounding right. I don't know if you can hear that, but it's definitely buzzing. So if we go down to 63, we can avoid that buzz. And that keeps our range from 0 to 127, so we can add wavetable to wavetable. And now it sounds clean again. And now I have to turn it down or I'll drive myself nuts. So that's the reason why we had to use 63 and not 64 over in here. Just to get a little headroom. Because if you're doing things where you're adding two wavetables together like this, and you got 127 plus 127, what does that get you? 254. Yeah, it seems to go just a little bit outside the headroom space of the DAC. So maybe it's really adding 128 to 128, which would give you 256. Yeah, that would mess things up. So 63 seems to work. 64 is too much. Now, had I taken these numbers and cut them in half and then added them together, maybe that would have been all right. But it's wavetable 0, you know. Anyways, there's a little hackery going on here. Hackery. Let's see what else we got here. I want to see where else there's a DAC right, just in case I missed it. Here we go. It's wave generator. So here, wave generator is also taking two wavetable positions and adding them together. That's also doubling the output. So that's another reason why you can't just use something like 255 as the absolute value for the maximum for the waveform. Because if you're adding wave tables to each other, that's just going to mess things up big time. Any questions about this? Everybody okay with the final project? So now that we got the evaluation thing done, why don't we take a little time and look at the final? I think that's the right thing to do now. So
Professor,
yes, sir.
for the evaluation, those two links are the same link, right? They're not two different links.
They're supposed to be two different links. They're supposed to be. This says view evaluation link, and this is the number I got for the lab. Is that the number you see?
Oh, is one for the lab and one for the class?
Exactly. So they should be different in theory. Different links, right? Because this one says L01. And then there's this other one here, and it says 801. So these are different numbers. And, you know, the ELEG number is kind of, I don't know. This is this, right? What is that? The CRN number? I'm not even sure. That must be the CRN number. And then I think the CRN numbers are different for the two different courses, right? So this course has a CRN number L01, and this one has a CRN number 4801, and they are different numbers, I hope.
If I just refreshed the screen, it was giving me like an error and reloaded like the same page.
Oh.
I have them both now.
You do? Okay, so they are different. They look like the same evaluation, I think. Maybe they ask the same questions, but they are supposed to be targeting two different courses, although in my view, they could have done just as well if they just lumped both courses together. But I don't know. I mean, I could sort of see their point. The lab is really a different course than the lecture, I guess, right? Because you get in with your hands on kind of thing. So there's that. And then there's this final. And I made a note about where we left off. Is it possible we got as far as question 57? You guys tell me. These all look very familiar, but of course, why wouldn't they look familiar to me?
I think we got to question 50.
Question 50, was it? Okay. Let's see. Yeah, this is stuff we all did. What's going on here? Geez, we did all this? Boy, are we industrious. We're halfway done. Question 49. Yeah, I remember doing that. So there's question 50. So if I want more current than 500 milliamps from a ULN 2003A, stacking one chip on top of another, both electrically and physically, should get me it. This is not decent English, but what are you going to do? This is That's what happens when engineers make up tests. So can you stack ULN 2003As? You know, one thing you could do is you could say ULN 2003A stack. See if anybody's like stacking these things. And presumably you can see one stacked on top of another. Here they are. These guys are daisy chained with one another, but there should be an example where you actually physically stack the chips one on top of the other. And that is an interesting way to go because you can actually do that with these chips. And then you're basically running your transistors, your Darlington transistors in parallel. And so that's a trick. ULN 2003 data sheet. He's not giving me the data sheet. Let's see if I can just zoom in on this. He's not letting me zoom in either. This is just annoying. There should be like a data sheet for this. All right, so what you want to do, start with the dip and just put another dip on top of this dip and then solder the pins directly to one another. And that will double the current that you can draw. You could always change the chip and get something that sinks more current, but we have these in the stock room. And if you needed an ampere out of an Arduino, well, put in these Darlington transistor drivers and that'll give it to you. And you'll take an input like this and it will allow you to float the driver voltage. And so that's cool. And it is here's the pinout. So now you can see why you can stack one on top of the other. Its outputs are being driven so that they are in tandem with their inputs, and the ground and common, these things are going to be the same for both chips. And so there's no possibility of a short circuit if you put an input in that's going to be a 0, the output will come out as a 1 and vice versa. So that's a nice way to go. If you're wanting to increase power to 2 amperes, I guess you could stack 4 of these things, but at some level you want to call it quits and just buy a different chip. And it's not meant for driving fast changing signals like the 4921. It's meant for going into and out of saturation like a switch. And you're going to be wanting to operate these transistors in saturation mode. So it's very good for a stepper motor that needs substantial current. Pins 2 and 3 enable interrupts in hardware. Is that right? Pins 2 and 3 enable interrupts in hardware as shown here. As shown here? Where's my picture? Did I mess that up? So I got a problem with, I've got a blemish on question 51. Let me write that down. No picture. That's too bad. If you wanted to see the Arduino Uno pinout, you could look at pins 2 and 3. And here's 2 and 3. Right in through there. And you can see it says interrupt 0 and interrupt 1. So if you're ever in doubt about something like that, you can always Google it. And actually, this is kind of a really nice, of all the diagrams I've seen, this is a really nice one. This has there's the MOSI, the MISO, the serial clock, the serial select. There's the PWM pins. That's cool. Let's see what else we can see that's interesting here. Timer 0 and timer 1 inputs for 4 and 5. I mean, you can repurpose these things and use them as inputs or outputs. You can use them as digital inputs, just read them. They're digital outputs. Or you can use them as something that'll reset your timer with an external interrupt that's asynchronous. That's cool. There's a serial clock and serial data. That would be for the I2C bus. So these 2 pins, pins 27 and 28, that's your I2C bus pins. And then these pins, 10, 11, 12, and 13, that's your SPI bus. Your in-circuit programmer at ICP. There's your interrupt pins right in through here. And here's the transmit and receive serial port, pins 0 and 1. You can reuse these for input and output, but what happens is it messes up your ability to download if you're not careful. I'll just put this off to the side. Let's go to the next one. What is this line processor? Any ideas? I start calling on people, I think. Alina. Alina March, are you there? Raza. Kamantija? I don't know how to pronounce your name, sorry. How about August? Are you there?
Sorry, you see August?
Yeah, August.
Yeah,
You okay? So August, what do you think about this line processor?
In response to answer the question, or just in general?
Yeah, I mean, what does this inversion of control mean?
I'm not really sure.
That's a new term for you, right?
Yeah.
Okay. Fair enough. So inversion of control is a style of programming where you expect a callback. You provide an implementation, and then if you wanted to do something like demand that the line processor do a process, someone called the line processor will read a line, a string, and then call process, and they'll expect the implementation of the process method to do something with that line that comes in. So that is an example of inversion of control, because we're providing an implementation of the process, but we don't know who's calling it. So, whatever the master program is that's calling it, they have control, and we're giving that control to them by providing an implementation for the line processor. So you might see that if you had, for example, a button that somebody clicked on, you would implement that button by implementing an action listener, and the callback for the inversion of control on the action listener would be action performed. So when somebody clicks the OK button, then the OK button knows how to process itself. So it has its own implementation for the action performed, that is the click, and then does the OK thing, whatever that may be. We can have an example, I think, of this in the so-called runnable class. So when we look at, for example, GUI run methods, right? Here is an example of the run functions that you can run into. So here's a run button. And the run button apparently knows how to run itself. And so what we have here is, let's find the main method, because usually there's a main in here for testing. So here's a run button, and what it does when somebody clicks the OK on the run button is it prints OK button. And when somebody clicks stop on the run button, it does the cancel button thing. And so you don't have to visit the code in multiple places to find where the implementation for the button is. So when we run the program, we should see buttons that know how to run themselves. So here's a start and here's a stop, and they both know how to run themselves. So the basic idea here is that if I were to add an action listener and then put the action performed for the run button somewhere else, I'd have to visit the code in that other place, wherever action performed is implemented, and then proceed to do the right thing. So then I'd have to have a dispatch that says, well, if it's the OK button, do the OK thing. And then if it's the stop button, then do the stop thing. And if it's this button, then do the that thing. And that goes on and on and on. So by using this little isomorphic mapping between the action that's performed and the item that's actually doing the action, we can isolate where the implementations for the action are. And that's what this does. And so we're providing a callback. We don't know who is calling the run button, but we do provide a run method. And that run method enables us to effectively find a way to embed a command into the button. And it doesn't have to just be a button, right? You can have any one of a number of things. Here's a run color chooser. And presumably when somebody runs this, they'll be able to get a color out of it. And we can hide the complexity of the color chooser from the user. So I can choose a color any way I like, using hue, saturation, and value, using hue, saturation, and luma, using RG and B, using cyan, yellow, magenta, and black. And then when I click OK, he comes back with the actual color in red, green, and blue. So I can make a new instance of the color and maybe color in a large swath of an area for my color picker. Sorry about that. So the basic idea now is that inversion of control is going to give me an opportunity to hide the complexity of what's calling this from the actual implementation. Then we've got something here. This is another thing. It's kind of like inversion of control. It's the interface stoppable, something that can be stopped. Has to have an implementation of the is stopped method. So to determine if something is stopped, right, you have to get a true or a false when you invoke is stopped to see if it's stopped. And the program has to figure out what it takes to stop it. Now the question is it going to stop it, or is it just going to tell you if it's stopped? We're not sure, but we know that if it is stoppable, it's up to the program to figure out what it takes to stop. So the answer to that one would be true. So stoppable is something that you can embed inside of these programs. And now we have this very simple interface, and I do like a simple interface that lets us implement a whole bunch of things that are perhaps stoppable. You know, the decision about when to create one of these interfaces will live with you for a very long time. It's a basic problem in software engineering design. You can create a little decision today that has a big impact tomorrow. And so when we think about something like an image processor, and we have an interface that does the image processing, like here's an image processor interface, right? This is a really simple sort of thing, right? This is an example of inversion of control. You're creating an operator, and it takes in an image and it returns an image. We have no idea how long it takes to do that process. We don't know how complex things are. And if you're building an image processing application with a lot of operations, you can look to see who's using it. And look at this. This is all over the place in my code. We have hundreds of imports, hundreds of implements. It's like all over 358 usages, and making one change like this would break an awful lot of code if we didn't go through and repair it in an appropriate way. So we got video processors, all kinds of interesting and wonderful processors just from that one interface. So it seems like it's a simple interface and it doesn't really, do anything, but it's subtle, right? Because so much depends on this one interface. And if you decide, well, gee, I don't want that kind of image. I want a Hubble image that's got floating point numbers. I want a floating point image. And you're like, well, this doesn't do that, right? This kind of image is not that kind of image. And all the image processors that implement it would have to change anyway. So you'd need a new interface and then new implementations for the new image type. So that's a form of inversion of control. And it isolates you from the graphic user interface pretty well, because this is going to be your business logic. And the stuff that, has swing in it or AWT or some sort of HTML interface is not going to impact the business logic and the way images are processed. Now here's another blemish in the code, another bug in the final. Question 54 has got no picture again. No picture. And that's a problem, and we're going to have to fix that one. So I'll go back through it and make sure that that's fixed. Let's look at this question 55. I think that's more of an Arduino question than anything, really, because, well, what's up with this and percent? What's that? What's that mean? Let's see. John Fee, what is that and percent for?
Is it a bitwise and?
No, that's a good question, and it isn't. This is the address of A, and this is the address of B. So normally, if I was in a Java program and you ran something like this, it wouldn't impact A and B at all, right? Because you'd be making a copy. You'd call by value, and a copy of A and a copy of B would be passed in. And anything you did to A and B as they came in would effectively have no impact outside of the method swap. But here it does, because we have access to the address. Or do we? And the answer is yes, we do. And because of that, we have this unique ability to work with scalar data types as though they were references in Java. And we can effectively call swap A and B and have A and B swapped. That is, we can swap the values of A and B. Because ampersand A is the address of A. So you're swapping addresses. Swapping addresses. So that's the C versus Java thing. You don't get to do this, right, in Java. That, if you have an int, it's called by value, not by name. But here what we're doing is we're calling it by name. So let's look at this. What do we got here? This is looking like a turning motor. Very cool. GIF animation. So finally got some pictures that worked here, which is sort of nice. So then it says here, let's see, lead unipolar driver. Unipolar control is the most simple and cost-effective way to drive a stepper motor, but results in approximately 30% less torque in comparison to the nowadays widely used bipolar driver, since the cost advantage is very small. Due to the cheap integrated circuits, bipolar drivers are now used in most new applications. So do you really need a microcontroller to generate this sequence? Let's think about this. 1100, 0100, 0110, 0010. What is, and look at these numbers that are coming out. 12, 4, 6, 2, 3, 1, 9, 8. What is this? Let's go to someone new. Shamrock. What is this sequence of numbers?
Let's see. I'm not exactly sure about the sequence of numbers. I know you need a microcontroller to shift the one value over every single cycle, but
are we really shifting the one value? I mean, it went 1100 and then it went 0100.
But isn't the column going like a 1 on the left column and then 2 ones on the right?
The sequence, the sequence is 12, 4, 6, 2, 3, 1, 9, 8.
Oh, those are the representations of each number, isn't it?
Yeah, so this is the binary, and here's the decimal down here at the bottom. And so you want to generate that sequence and then go back to the beginning. So that's a finite state machine, but it's a special degenerate finite state machine. What kind of finite state machine is that?
That would be synchronous.
It is synchronous, but there's another name for it. There are lots of different synchronous finite state machines.
We're talking about if it's a Moore or Mealy machine.
Not necessarily. It could be either. You could implement this with either Moore or Mealy. If you did this, you could make it synchronous or asynchronous. So then the question is, what kind of finite state machine is it? And the answer is, it's a counter. It's a counter because it never visits the same state twice. So this is essentially a simple counter. It's just not counting ascending. And it doesn't visit every state, right? Because there's no state 0 here. It would normally be something that includes 0. There's no 10 or 11, 13, 14, 15, 16. Oh, I guess you would stop at 15. So yeah, if you look at it that way, this is a counter. And if you were a digital design 1 student, and I think you were, and if you were in my class, and I think you were, then you would know how to design a finite state machine like this. And I think you do. I think you do. So in fact, you get the remapped excitation table inputs, and you show how we go from one state to the other for A, B, and then of course A inverse and B inverse. And then in principle, you could do the whole thing with a couple of flip-flops. And you don't need a microcontroller for that. You need like 2 flip-flops and some random logic, and you're there. And that's and that's going to give you the ability to control the stepper motor if you can create a clock for your finite state machine. You could use a 555 timer for that with a little diddle pot, and then you could choose how quickly the stepper motor turns. Because if you ran at full speed, it would run at several megahertz, and motors don't step at several megahertz, at least not the ones that we have. So any one of a number of approaches can be used to implement a finite state machine. Certainly you can use a microcontroller, but you do not have to. You could do it with an FPGA if you really wanted to. Why not? Would be a DE2 board driver for the stepper motor. You could do that. That's doable. Let's see, what do we got here? Modern RC servo positions are not defined by the pulse width modulation duty cycle, i.e. on versus off time, but only by the width of the pulse. That is on versus time off. Only by the width of the pulse. So all I have to do is change the width of the pulse, and that's going to change the RC servo position. So if I have a servoed system, I got to change pulse width, but not duty cycle. Does that sound true or false? We did this with servos, right? We had a lab on servos. What were we changing? I'm going to call on someone else.
Were we changing the amount of time that it took to make a complete rotation?
Well, we were actually changing the width of the pulse. Is what we were changing. So that is a true statement. If you take an oscilloscope and you look at what's going on to the control input on the servo, you'll see that the width has been changing of the pulse. Pulse width is changing. Let's look at question 58. Let's see. It says here, the following code, serial up again, has to be used at the start of every loop. Actually, it says very loop. That's a typo, another blemish, but it should say every loop. 58. Typo. Got to fix that. Is that true? Let's see. Ugo, you're with us still. Is that true, do you think? T. Young, what do you think?
Is that true?
Yeah, it is false. It is false. You don't use a serial dot begin at the beginning of every loop. You put it in the setup.
I didn't know. I didn't read that. It was every loop. Sorry.
Yeah, every the part about every loop is a little mangled because it says very loop, but it should have said every. There's a small typo. Let's look at question 59. When I assume B is of type byte, then I say B shift 1. It gives a numerical result that is the same as using B equals B divided by 2. Lena, is that true, do you think? How about you, August? What do you think? August Feliciano. Are you with us? John Fee, we're back to you.
I think that's true.
Yes, it is. That is correct. Because you're shifting to the right by 1, and that is a divide by 2. If I shift to the left, it's multiply by 2. So divide by 2 is easily accomplished with a shift to the right. Let's look at question 60. Interrupts can be sent by hardware or software. Let's see who hasn't gone. Shamrock.
This is true.
Yep, that's true. That's true. I think we might have time for 1 or 2 more questions. Question 61. In the following code, SPI setup mode, SPI mode 0, set clock, divide by 8, set bit order, MSB first, and then begin. What will the SPI clock be? Let's see, who knows? John, are you still there? John
Me?
V? Yeah.
Oh yeah. Would it be 4?
So what's the Arduino clock rate?
Is it 16 megahertz?
Yes, and then it says SPI div 8. So
So
if you
2.
2 megahertz,
Yeah.
that's it. That's it. So your SPI clock is, it can't really run at 16 megahertz for many SPI interface things. So you slow it down a bit. So what do we got? Looks like we are up to question number 61, which means we are 61% through. I'm just going to write question 61 was our stop point. We'll be able to pick this up in our next exciting microprocessor class because we are out of time, which you can see here. So good luck on your final project. If you've got questions, take them, write them down and bring them with you to the extra help session, which we will have on Wednesday at 10 o'clock, which is actually the day in which it's due. So if you're stuck, come to class at 10 and we will try to get you unstuck. Thanks very much and have a good day and stay safe.
Thanks, Professor. You too.
Yeah.
Thank you.